for deflection of beams. So this is the third chapter of Mechanics of Materials 2, deflection of beams. So in the previous chapter, we discussed the design of transmission, designs of transmission shafts, and the second part is combined loads. Now we're going to, we're going kind of back to another topic which is related to beams. So for this chapter, so deflection of beams, we are interested to determine the maximum deflection of a beam under a given load, since the design specification of a beam will generally include a maximum allowable value for its deflection. So just imagine if you are driving a car, let's say over a bridge. That bridge has a certain very small deflection, and you're only allowed to a certain deflection so that it would not fail. Now, once you overshoot that allowable deflection, your bridge might fail. So it's important in terms of design criteria to determine what's the deflection given a certain loading condition. Now, if you talk about deflection, let's say if we grab this piece of ruler right here, which is a steel. So we have this ruler. We push it down, so that's what we call deflection. And we can easily imagine that deflection could change. It depends if this roller right here is plastic, if it's steel, if it's aluminum. So it highly depends on material. So you can see later that once we calculate for deflection, it would be highly dependent on the material property. Now, what are the topics under deflection of beams? So we have deformation under transverse loading. We also have statically indeterminate beams. We have singularity functions to determine slope and deflection. And what do you mean by slope and deflection? So if this is our beam, and let's say we have a support reaction here, let's say it's cantilever beam, so I'm holding it here. I have a force going down. So deflection is how much this point at the end, for example, how much this point moves from this point up to this point. So that would be your deflection. Now, how about your slope? Your slope is, you can imagine that if this is bent this way, it has a slope at every point, so that you can calculate what's the slope of the beam at a certain direction. And we're going to discuss that later in the next slides. So we have singularity function determines slope and deflection, and then we have method of superposition. So for today and for Monday, we are only going to focus on deformation under transverse loading, which involves second order differential equation, fourth order differential equation, which we are going to see later. So now let's imagine, again, going back to our beam example. So it's changing it to black. So let's say we have a beam. Let's say this is fixed at on the right side. So we have force P. Now, once we apply force P, this beam right here could deflect like this. And of course, this deflection is exaggerated. It could be really small that you might not even notice it with your naked eye. All the deformation, take note that deformation happens in the elastic region. And what do we mean by elastic region? If you go back to the concept of stress strain curve, so right here, so your elastic region is this very small area of your stress strain curve, which means your strain, which is your X value here, is extremely small. So you don't allow any permanent deformation to your material once you apply this type of loading. Now, going back to our beam on the top here. So we applied force P, and your beam could deflect in this way. Now, in beam deflection, we can assume that at this point, so we can first define our reference axis. So we can say that that's Y, and that would be, let's say, our X axis. And this would be our 0 point. So that's our reference point from 0 into, let's say, a certain value of, let's say, X. Now, you can easily imagine that if this is Y, and this is X, and our beam deflects down, we have a change of dimension along Y. And that's what we call deflection Y, which we're going to talk about later. And that deflection changes from one point of the beam to another. And we can see as we move from left to right, from this point, this point, this point, this point right here, you can see that this Y value here, or we can call it negative Y because it goes down. So you can see that it changes from one point to another. So let's give another example. So let's say we have 2 pin connections. and we have a beam. Let's say we apply a load P, for example, at this point. And once we apply a load P, we can imagine that our beam will deflect this way right here. Now, once it deflects that way, you can tell that you have deflect. You can first define what's your axis, what's your reference axis. So in this particular case, and yeah, I like purple for some reason, so that's Y. And let's say that's your reference axis 0, so that's our X. So this would be our 0 point. And you can see that, let's say at X is equal to 0, you can tell that you have Y is equal to a positive number at this specific point. Okay, let me just. Okay, yeah. So you have deflection of Y at X is equal to 0. Now, as you move from left to right, you will see that your Y changes. It could be positive, it could be negative. So that's deflection Y. How about our slope? What do you mean by slope? So imagine if that's the deflection, and we can, for example, write it in our reference axis. So that's X, that's Y, and let's say that's the deflection of the beam, not necessarily on top, but let's say this is the deflection. And again, your Y is this point here, that's your Y. And the slope of your beam is changing from each point. So for example, you can put a tangent line to each spot, and you can see that at this point, at that point, at that point, there's a slope, which we can call dy over dx. So that's the slope of the beam, which also changes from one point to another. So we have two things. We have y, which is the deflection along your y-axis, and we have dy over dx, which is the slope of our beam. Now, dy dx, if you check other books, sometimes they also call it theta as a function of x, which just means that if I'm going to apply a tangent at a certain position, I have a angle theta which changes as we change our x. So now we are interested in these two different with the deflection and the slope of the beam, because this one describes if your design can. That's part of the design criteria, let's say, when you are designing for a bridge. Now, if we have dy and dy dx, imagine that the dy values here, you can fit it with an equation. So you can have y is equal to something as a function of x. So this is a function of x, and you have equation that defines this curvature. And similar for your slope, you can have an equation dy dx is equal to something which is a function of x, because it changes from one point to another, that defines the slope of your beam. So technically, you can see that your deflection and your slope could be defined by an equation. And the objective of this particular topic is to get those equations. What's the y equation, so that I would know what's the deflection at any point of my beam, or I can get any slope at a certain point along my x. So now, the most basic equation for our deflection of beam is this one. I normally discuss the derivation of this one, review it in the book. Normally, it's not included in the exam derivation for sure. I normally derive this, but in our class, we are a little bit behind. But you can review the derivation for this equation. Now, this equation just tells you that your d squared y, so that's the second derivative of your y, is a function of your moment divided by e divided by I. And we're going to discuss it more. So we have a general equation which relates the second order differential equation with m sub x divided by ei. And what do we mean by m as a function of x right here? Now, remember a beam. Whenever I see a beam, at least for me, when I did my undergrad, whenever I see a beam, I imagine I should draw a shear and bending moment. That's the first thing I can think about. That, okay, that's the most basic thing. I have to draw my shear and bending moment diagram. Now, what is m sub x? imagine your moment is changing with respect to x. So you have to get a along your beam, right here, you have to get your m and how your m changes with x, which we are going to discuss later. So, but this is an equation that we have to establish later on. Now, we have a moment equation. We have a second order differential equation on the left. Now, the important thing for us is to get dy over dx because this is the slope of our beam. That's very critical in terms of design. How can we determine the slope of the beam? We can get the integral of both sides of the equation so that we can eliminate this square value right here, and then we are left with dy over dx, which is the next slide right here. So you can see that this is just transposing E sub I, and E is a material property. It's the elastic modulus of your material. So everything depends on your material, EI. So this one is transposed on the left side, and once you transpose it to the left side, you integrate both sides of the equation. So this one becomes just dy over dx. This equation here is now under the integral, and of course EI you already transfer it to the left side, so you have mx dx from 0 to x plus c1. Now you have a constant of integration whenever you integrate, so we're going to put here plus c1 for now. So from d squared y dx squared, so we have m sub x ei. So now we have our slope equation, which is this dy over dx, is equal to, I'm not going to put 0 to x for now, but yeah, we can put 0 to x mx dx plus c1. So we have a constant of integration from there. Now we have a slope right now, but we mentioned we're also interested with deflection, which is y. So how can we determine the deflection? But before we determine deflection, I'm sorry, I haven't discussed this one. So this dy over dx here, it's just the slope of your curve. So if that's our point, so at any point in x, if that's the deflection of your curve, it has at some point, it has a tangent line. You can apply a tangent line right here, and whatever angle is that, that's your slope. Now, again, this theta sub x is just equal to your dy dx. That's the same thing. So that's basically this equation here. We mentioned it's not just slope. This is slope of your beam. Now, how are we going to get the deflection y? So again, if we have a y in x, and then this is our beam, so this deflection here, so if this is the ruler, this deflection here, this change along y-axis, that's your deflection y. And if we're going to look at our equation right now, again, we can integrate this equation here, and then we are left with y. So we can now integrate this second equation here to get our deflection. So once we integrate that, we are going to get following equation. So we have now, instead of dy over dx, we now have just y. Now we integrate it twice, so we have integration from 0 to x dx. You have from 0 to x, again, mx dx. So you integrate this equation here twice, and then you are left with two constants of integration. So now your c1 becomes c1x. Now this one becomes c2. So let's write that down. So now we have, so I normally write it in this way. So we have e I y is equal to 0 to x. Now, earlier I also did the integration for my m dx, and everything is dx. So I normally write this way, other than this one on the slide, plus c1x plus c2. Now, we already established our equation, and we are going to worry about m sub x later, but our problem right now is how can we determine C1 and C2? Now, C1 and C2 are constant of integration, and you can determine it by applying boundary condition. And what are boundary conditions? So So boundary condition are the following for the different types of beams. So let's say if we have simply supported beam, so like this one, so we have at point A and point B, let's say you have a pin support, you have a roller support right there. Imagine that your beam could bend this way. And since they are connected at A and B, imagine that if this roller right here is connected to pin right here, is connected to pin at this point, if I apply the load at the middle, it will not move. Your Y will always be zero. So unless you break your pin, of course it will go down or up. But in this particular case, if this is supported by two pins, if I move this down, your Y wouldn't change. And same thing here. So if you have simply supported beam, which is like this one, you can see that at point A and point B, your Y is equal to zero. And how this boundary condition will be useful to my equations right now. If my Y is equal to zero, I can apply that boundary condition. I can substitute Y is equal to zero, and then I will have equation which relates C1 and C2. But again, that's just one boundary condition. Sometimes, or most of the time, you have to apply two, or sometimes you have to apply four boundary conditions. But right now, that's a function of your boundary condition to zero out some of the values and calculate your C1 or C2. So that's the first boundary condition. How about the second boundary condition? So if you have it's not moving. Okay. So if you have a overhanging beam, so you have your force is applied this way, and you can see that this connections here at point A and point B, it still lies at Y is equal to zero. It doesn't move. It only deflects at the middle. It has a deflection at the middle. It has deflection at the end, but at connections A and B, it won't move. So your Y will always be zero at point A and point B. It doesn't move whatever you put a load right there, unless you break the pin, and of course that would move your beam. Now the third case right here is a cantilever beam, and so for a cantilever beam, so it behaves a little bit different in such a way that you can have two different assumptions at your reactions. Imagine at point A and point B, we only assume that your Y is equal to zero, and here Y is equal to zero. Now, if you have a fixed support like this, which is a cantilever beam, specifically on this left side, it's not just the Y doesn't change, the slope is also zero. And why the slope is zero right there? So just imagine a cantilever beam, this, and let's say it bends this way. Now, let's say this is your support A. Now, at support A, how can you determine the slope? So the slope of the beam, I can write a tangent line, and I'll try to check whatever my slope is, and of course at the end I will reach to the flat line here, which corresponds to zero slope. So for cantilever beam, at this point A, it's not just your Y is equal to zero, my slope is equal to zero. And why is this important? So if you look back to this equation here, slope of the beam, if I'm going to use my slope is equal to zero, you will imagine that this would become zero. I have a certain values of my M as a function of X, and then I have C1, so I can calculate my C1. So I can determine what would be my C1 or my constant of integration. And take note, this is a constant number. It doesn't change when you are moving from left or right of your beam. Any question at this point? Everything is clear? Clear so far? So that's the concept of beam. So again, everything starts with this moment curvature relationship. You have moment. Your objective is to get the slope at every point of the beam, or the deflection at every point of the beam from 0 up to X, or 0 up to the length of your beam. Because again, you may want to determine what's the maximum deflection of this, for example, ruler from left to right. If it's bent this way, it's obvious right here. But if you have complicated loads, it's not obvious because your beam could bend this way. It could be it could go up and down. It's not just as simple as pushing it down, and that's my curvature. Now, in order for us to show this M sub X right here, because so far we discussed slope, we discussed deflection, we discussed this this boundary conditions. The next thing for us is how can we determine M as a function of X? And just imagine if you have a moment, And imagine you have shear and moment diagrams. You are developing shear and moment diagrams. You can fit an equation as a function x to define your let's say your moment diagram. So that's kind of how it works. But let's look at this particular example and see how can we determine m as a function of x. We still have around 5 minutes, but yeah. So now, and what we're doing right now is what we call second order differential equation method, which means that, we can see it from the equation that it is second order. So yeah. So now let's look at this concept application number one. So we have a beam with a length L. We have a force P. You have a cantilever beam, which is a fixed support. So we know that at point B, so I'm going to write it down. So we have A, you have B, you have L, and you have force P. And you know at this point B, based on your boundary condition, y is equal to 0 at this point. And you also know that your dy over dx is equal to 0. Before solving any problem, the most important thing is putting a reference axis. And sometimes, most of the time, it doesn't matter where you put it, but most of the time, it's either left or right. And most of the time, one will be super easy. The other part will be much more complex. And what do I mean by reference axis? So I can assume that my 0 point lies right here. So that's my 0 point. That's my y. That's my x. Now, you can also put a reference axis right here. It doesn't matter. You should still get the same answer if you change the reference axis. I can put that this is my 0, and that's my 0. That's my x. That's my y. And sometimes one will give you a very straightforward answer. Another one will give you a hard time in order for you to determine what would be the answers. But uh, for our example, let's use this reference axis here. So let's remove that one. Okay, so the question here is find equation of the elastic curve. And what's elastic curve? So in this particular case, the elastic curve that the problem is talking about is, imagine that your beam could deflect like this. So you have a certain value of y. So you need to determine an equation, y is equal to a function of x, that describes the change in y as you move from 0 into x. So that's what the letter A asks you. So find the equation of the elastic curve. And how can we determine that equation? If we go back to this slide right here, that's the thing that we're looking for. That's the y that we are looking for. Now, how can we arrive at this equation? I mean, there's already two complex here. We move right here, and we have to start in the second order differential equation. So first, we have to get the equation that relates the moment in terms of x, and yeah, we can do it right here. So how can we do it? So first thing is we have to, because we're talking about a length x, so we have to slice our beam, for example, at this point, and assume a length x. So x could be it could be up to this point, up to that point, up to any point in between A and B. So I can cut my beam right now, slice it, and get some equations. So I cut a certain length of x. Now, after I cut it, I know that I have force P right here. And when I cut this beam right here, take note that to balance this one, I have to get my shear stress right here, and then I have a moment. Now, how can so take note, if you only have P on the left side, it's not balanced at all. You have to kind of balance the thing out. So you have to assume this M and V right here, and I'm going to show it to you shortly. This is one method. There's another method, which is just looking at your shear and bending moment diagram. So let's take a look at this one. So I can sum. So if I sum my forces, so my if I sum my forces along my x, or along my y, sorry, and which should be equal to 0, that would be, if I assume that the downward is negative, let's say negative P, and I have negative V, that's my shear right there, and that would give me a value of V is equal to negative P. So I have that following relationship for my V is equal to negative P. But we don't need V for now. We need M. So let's get the moment. So how can we get the moment at this point? So let's get the moment at this exact point. So moment at that point. And I think I'm going to repeat it because it's 1:55. I'm going to stop here. I'll because this will take a little bit long, and I have a meeting exactly at 2 p.m. and I want to have a few minutes break before I join the meeting. But any question at this point? So I'm going to stop here right now. And again, I just want to introduce the topic to you before we discuss it in more detail on Monday. So any question at this point? And I'm going to stop the recording. And I think someone raised his hand. So